Welcome back. Well, aside from checking what Möbius transforms do to the plane, we're also interested certainly in what various standard types of functions do to the plane, and that's what we're going to talk about in this presentation. We're going to take a look at the sine function, we're going to take a look at the square and the square root functions one more time. Square roots of polynomials, here's where it gets really complicated, but we're going to look at least one example to show how square roots of polynomials can be defined on a somewhat larger domain than would be obvious. And we will talk at the end a little bit about Riemann surfaces, which are a way to get around the fact that functions have, such as the logarithm, have multiple values. Okay, let's get to it. Well, let's see. We start with the sine function, and if we're looking at the sine function, then u plus iv equals sine z, where z is x plus iy. We can break that up into sine x cos y plus I cosine x sin y, so where we're mixing the hyperbolic sine and the hyperbolic cosine in here too, and that's just straight application of the additive identity for the sine function. But that means that the real part of the sine function is sine x cos y, and the imaginary part of the sine function is cosine x sin y. Okay, a standard way to visualize what a transformation does is to analyze images of horizontal and vertical lines. We've already seen how, as we work with Möbius transforms, looking at circles and lines has helped a great deal. Well, it turns out circles in general are quite unhandy. Möbius transforms are one of the few exceptions where we can actually work with them. But lines, I mean, that's the easiest kind of input you could have, especially when they're horizontal and vertical. And if we have that, well, if we know what horizontal and vertical lines do, we have a grid on the domain, and if we know where that grid goes, we pretty much know where everything else goes. So let's see, we're talking in this first example here about the image of the vertical line x equals c1, where c1 is between 0 and pi halves under the function w equals sine of z. We actually are interested in the images of all vertical lines, x equals c1 of course, but if the real part as well as the imaginary part are both 2 pi periodic in x, and they are because the real part depends on x as a sine x, and the imaginary part depends on x as a cosine x. That means we really only need to consider one full period, negative pi smaller equals c1 smaller equal than pi. And what we're going to show below shows that we can actually restrict ourselves to the interval from 0 to pi over 2 because the rest is mapped to the same places. So for x equals c1, well, what can we get? Well, we remember what the sine function looked like, right? It was sine x cos iy plus cosine x sin iy. And so that means that u squared over sine squared c1 minus v squared over cosine squared c1, that's just cos squared minus sin squared. And we know that that's equal to 1. And that means that that is a hyperbola. Okay, that is something that you probably want to work out with paper and pencil, but it's not that bad. Just plug in u and v and do the cancellation. And we realize that's a hyperbola because c1 is a constant, right? And because of the squares in the denominator here, 0 smaller c1 smaller pi halves really covers all the possible non-zero denominators. Okay, so the question then is, what about x equals 0 and x equals pi over 2? Well, for x equals 0 and x equals pi over 2, with u being sine x cos y and v equals cosine x sin y, the images are u equals 0, sure, because that's when we have x equals 0, we get sine x equals 0. And v equals 0 because when x is pi halves, then the cosine of x is equal to 0. And cos and sin make sure that we sweep out those lines reasonably well. Okay, so now let's take a look at horizontal lines. Y equals c2, c2 greater than 0, under w equals sine of z. Again, remember, u was sine x cos y and v was cosine x sin y. So if you plug that in, do the cancellations, you realize that that must be equal to 1 by the trigonometric Pythagoras. And so that's an ellipse. So that means horizontal lines go to ellipses. And because of the squares, c2 greater than 0 captures all possible images except c2 equals 0. And well, then again, we have to ask what happens for C2 equals 0. But for C2 equals 0, we've got the line y equals 0. And when y is equal to 0, well, then v is equal to 0. And sine times cos sweeps out everything. So the image would be v equals 0. It would be the horizontal axis, the real axis. As an example, let's take a look at finding the image of the region 0 smaller or equal x smaller or equal pi over 2 and 0 smaller or equal y smaller or equal 1, which is a square under the function w equals sine of z. And we always remember that u is sine x cos y and v is cosine x sin y. Well, then the image of the first horizontal line segment, x going from 0 to pi over 2 and y being 0, well, that's just 0 smaller or equal u smaller or equal 1, right? And v equals 0. Okay, let's see. If y is equal to 0, then v is equal to 0 because sin y is equal to 0, right? And as x goes from 0 to pi over 2, sine goes from 0 to 1. Yeah, that is correct. And with y equals 0, cos y is equal to 1 to begin with. So, yeah, u goes from 0 to 1. Good. That's a horizontal line segment. When x is equal to pi halves, then of course we have to start going vertical. So for x equals pi over 2 and 0 smaller equal y smaller equal 1, the image of that I claim is 1 smaller equal u smaller equal cos 1, and v equals 0 still. And that is because, well, let's see, if x is equal to pi over 2, then cosine x is equal to 0, so that gives us v equals 0, right, throughout. And when x is pi over 2, the sine of x is equal to 1, and that means that this will go from 1 times cos 0, which is 1, to 1 times cos 1, which is cos 1. Okay, good. So another horizontal line segment. The image, now we're at the top right corner of the rectangle. Now we have to go back, y equals 1, and then x actually declining from pi over 2 to 0. Well, I wrote it in the normal way. That would be that u is between 0 and cos 1, v is between 0 and sin 1, and it's on an ellipse. Okay, let's see how that goes. Right now, when y is equal to 1, well, then we don't have any trick available. Cos y is cos 1 and sin y is sin 1, so nothing happens there that would allow us a cancellation. X going from 0 to pi over 2, that is a quarter rotation, right? Yeah, that would be a quarter rotation. And so that's a quarter rotation on an ellipse where the radius in the x direction is cos y and the radius in the y direction is sin y. So that really would be that quarter of this ellipse down here. And now we're at x equals 0, and we need y to go back from 1 to 0. And that gives us u equals 0 and v going from sin 1 back to 0. Let's see how that goes. X equals 0 means u equals 0, and cosine x will be 1, so we start at sin 1 and go all the way to sin 0, which is 0. So yeah, that works out. And that is not a horizontal line segment, that's a vertical line segment. And there we go, it's a vertical line segment. So basically what we have is that this rectangle is being turned into a quarter of an ellipse with appropriate radii. Okay, some other functions are now simply, and I don't mean that to be insulting, it's I guess it's simply a way to structure your memory to dispense with too much memorization and with too much worry about these things. The transformation w equals cosine z, that's simply the decomposition where you map z first to z plus pi over 2, and then map that to sine of z plus pi over 2, which is cosine z, using the appropriate trig identities. And that means the effect of the cosine transformation is essentially the same as that of w equals sine z, except that all the input is first shifted to the right by pi over 2, that's this addition, and then it's processed by the sine function. Similarly, we can dispense with sinh and cos. The transformation w equals hyperbolic sine of z, that's the transformation w equals I times sine I z. That's one of those identities for the hyperbolic sign, right? And so that effect is then essentially the same as that of w equals sine of z, except that the input is first rotated by pi over 2, that's this multiplication by I. Then it is processed by the sine function, and then that output is once more rotated by pi over 2. Okay, cosh then, same story. Cosh z is cosine iz, and so the effect is essentially the same as that of the cosine function. The input of the cosh function is first rotated by pi over 2, and then that result is processed by the cosine function. Now, I'm not claiming that that's going to be trivial, because in fact all those compositions, if you have to execute them to draw the right picture, will take some time. But that is really all it takes. As soon as you are comfortable working with these kinds of compositions, you will just be able to take an input picture, and as long as the function isn't too complicated, you'll be able to turn it into an output picture. Okay, let's take a look at z squared and the square root function. Well, for u plus iv being w being z squared, we've already shown in an earlier presentation that u is x squared minus y squared and v is 2xy. Okay, so we know that w equals z squared stretches a region in the radial direction because the radius is squared, and it stretches and translates into what we might want to call the angular direction, and that's because the argument for every point is doubled. What we're going to analyze here is the effect on specific shapes, and specifically we're going to talk about stuff that works with vertical lines, of course, and then we'll just have some neat animations also. So as long as we have the right branch available, everything we say about the square function works in reverse for the square root function, right? Because that's just the inverse. So let's take a look at vertical lines, the images of vertical lines under the square function. Well, when x is equal to c and c is equal to 0, we obtain that the output is c squared minus y squared in the real part and 2cy in the imaginary part. And if we just go ahead and eliminate the y, I think that's what we want to do there, that would mean v squared is 4c squared y squared, or y squared equals v squared over 4c squared, and that means that u is equal to c squared minus v squared over 4c squared, and that's vertical lines are mapped to parabolas that open to the left. And notice here that because everything is getting squared, that there is no difference between c greater than 0 and c smaller than 0, at least in the image. And that is because both the left and the right half plane are mapped onto the whole plane by w equals c squared, if you want to look at it that way. If we want to animate that, now we have to realize here that, of course, the function w equals z squared just takes a vertical line and outputs a parabola. But a continuous translation from one to the other is actually rather pretty if we start with a vertical line here and then just increase the input to z to the 1.001, 1.002, 1.003, and so on. We get a continuous way in which this line actually is being deformed into a parabola, which is kind of pretty. The interesting thing there is, if you take a line from the left half plane, the transition actually is not continuous at all, because basically all those functions 1.0 xz to the 1.01, z to the 1.02, and so on, well, that's where you're going through a branch cut, and so actually the line is cut into two pieces, and only when we hit z squared again are we reassembling stuff into a parabola. When I first made those animations, I was surprised by that, but it is kind of pretty to see that effect. Okay, if we're looking at vertical strips, then, well, if we're looking at the strip 1 smaller equal x smaller equal 2, then of course that becomes bounded by two parabolas, and if we're too close in on the animation, then it may even look as if that just remains a strip. Okay, we can see here that the size certainly is getting bigger as we get farther away from the origin, and so if we want to look at that under as we're zooming farther out, we can see that this really is an effect that keeps happening here, and we get parabolas that are farther and farther apart from each other the farther we go out and away from the origin. So I mean, stop that right here. Yeah, it's pretty well to see here that now that these are two different parabolas, and this region actually grows in diameter, if you will, as we go out towards infinity. If we're looking now at the function z equals w equals z to the 1/2, the square root function, if we're looking at the upper half of the unit circle, well, what does the square root function do? It just cuts the argument in half, and if we're looking at the unit circle, then there is some compression going on here, but the unit circle goes to itself, so that means all that happens is that the argument is being cut in half here, and of course the final image is the image of that upper half of the unit circle, which is right here. And if we now look at a circle z, absolute value smaller or equal than 2, well, that's where we can see that, of course, as we take square roots, the image also shrinks if the image has points of modulus greater than 1 in it. And of course, this is the image, and as I said before, the function actually takes the input, maps it directly to the output. The continuous translation is just something that I really like for facilitation of seeing how things are going on. Okay, now compositions with polynomials. Well, if you take a root and you compose it with a polynomial, that's really hard to describe because, I mean, the action of polynomials can be arbitrarily complicated. First of all, polynomials are pretty nasty by themselves, right? And then remember that through power series, polynomials can be used to approximate arbitrary analytic functions. So hoping that we can describe the action of an arbitrary polynomial, I think that's quite a bit too much to hope for. But because we have to deal, and moreover, because we have to deal with branches of the roots, the analyticity, it's one of my favorite words, the analyticity of even simple-looking expressions can be quite an issue because the polynomial may rotate around the origin several times, and so we might push through a couple of branch cuts, and that again makes things problematic. So what we could then, of course, do is we could factor the polynomial, because fundamental theorem of algebra tells us that every polynomial factors into linear factors over complex numbers, and then just deal with the product of transformations z minus z0 to the 1/2. That transformation acts just like z to the 1/2, branches and all. It's just that the branch point is at z0 instead of at 0, and points near z0 are mapped to places near 0. So that should actually give us a bit of hope. And so now let's just go ahead and analyze the function w equals z squared minus 1 to the 1/2. That function, if we're using separate branches of the square root function, we obtain that this function is z squared minus 1 to the 1/2, which is z minus 1 to the 1/2, z plus 1 to the 1/2. And the straightforward use of the branches of the square root function requires two branch cuts, and namely one for each of the square roots. And that means if we're choosing the right branch cuts, and what I'm claiming is by choosing the right branch cuts, we can make this function analytic for all complex numbers except the interval -1, 1. And that is actually quite interesting because branch cuts always go from the branch point all the way to infinity. This thing doesn't go all the way to infinity. So we have some work to do here. So let's let r1 to be the absolute value of z minus 1. Let theta 1 be the argument of z minus 1, where theta 1 is not equal to 0. So we're choosing a branch of the argument function where the positive x-axis is excluded. We let r2 be absolute value of z plus 1, and theta 2 be the argument of z plus 1 also, so that theta 2 is not equal to 0. And then we have that w is z squared minus 1 to the 1/2, which is z minus 1 to the 1/2, z plus 1 to the 1/2, which is square root 1/2, square root r1 e to the I theta 1 over 2, square root r2 e to the I theta 2 for the right kinds of points, which is square root r1 r2 e to the I theta 1 plus theta 2 divided by 2. And by choice of the branches, this function is analytic everywhere except when theta 1 equals theta 2 equals 0. We need to see that, so let's take a look at that. Okay, last sentence on this panel, I guess. That means that w is analytic everywhere except in the interval 1 infinity, because this is how it looks. Here is 1, here is -1, here's a point z. Now we find our theta 1. we find our theta 2, and we have excluded theta 1 equals 0, we have excluded theta 2 equals 0, everything else is fine, which means the function really is analytic everywhere except from -1 to infinity. All right, now let us do that. We can do the same thing. Now let us show that we can actually analytically continue this function also to the interval 1 infinity, so that somehow we can take this part that is cut out of our domain and throw it back in. Okay, so and that of course would prove that we can take W and make it analytic everywhere except in the interval -1, 1. Okay, so let's let theta 1 be the principal value of the argument of z minus 1, and let theta 2, capital theta 2, be the principal value of the argument of z plus 1. Then we have that g of z being square root r1, r2, e to the I theta 1 plus theta 2 over 2 looks just like W, but it's defined everywhere except when theta 1 equals pi or theta 2 equals pi. So this is the same function as what we had 2 panels earlier, only with a different domain. Anywhere of the places where either lowercase g or capital G is not defined, these functions give the same values. So yeah, formally g is equal to W everywhere except on the real line, therefore. So let's take a look at that. Here's 1, here's -1, here's a point z. Here are the angles theta 1 and theta 2 that we had before. And now, going to the principal values, we replace, and that would mean that we're excluding this line as well as this line. Now going to the principal values, we go to capital thetas, and now we're excluding this line, and we know that the functions are equal everywhere else except on those lines. Well, that means that W is equal to G for the real part of Z being greater than 1, and that means that for real numbers with Z greater than 1, we can set W equal to capital G of Z, and we obtain a function that is analytic at these real numbers, and that means the only numbers that are left where W is not analytic are in the interval -1, 1, and that one we cannot exclude at all. Yes, these we cannot remove. Okay, now the headline almost looks the same for this one, but now we want to analyze the function W equals Z squared plus 1 to the 1/2. Oh my goodness, that would mean we've got Z plus I times Z minus I, and we'd have to do all this stuff along the imaginary axis, or we could simply realize, and here again, this trick that we've seen a couple of times before already, of representing a function as a composition of stuff that we know works very nicely, because here we can now say Z squared plus 1 to the 1/2. Well, 1 is I to the 4th, so this is I to the 4th Z squared plus 1 to the 1/2, which is negative, that's the I squared. The other I squared is being put underneath the square, so it's negative IZ quantity squared plus 1 to the 1/2. And then I can pull a -1 out, so I get an I out front. So this is IZ quantity squared minus 1. And that's, of course, exactly the function that we had before, only that we first rotate the argument, then process with that function, and then rotate the output again. So that means that in order to describe this function, and I leave the remaining description to you, we would just have to look at this representation and then talk about what the domain and range are. And this one can be given a domain that includes everything except the interval from -I to I. Okay, so we're finishing with basically just a pictorial idea. Riemann surfaces are a huge subject that also connects complex analysis with differential geometry, and they're basically an idea to turn multi-valued functions into single-valued functions. A function like the logarithm, for example, will just not have a sensible definition at the origin, because no matter what we do, the logarithm goes to -infinity as x goes to 0 from the right side. But for the remaining complex numbers, the only problem with the logarithm really is that the argument is not continuous once we rotate around the origin one full rotation. Riemann surfaces are a way to fix these kinds of problems by replacing the complex numbers, which are the domain of the function, with a more complicated structure on which the troublesome parameter, which in this case is the argument, is actually continuous. Well, how do you do that? What if we did not have a flat plane, but instead something like a spiral staircase. Basically, the angle of the argument would still describe how far around the staircase we are compared with the starting position theta equals 0. But now, just as it happens in a spiral staircase when the argument increases by 2 pi, which would mean we fully circumnavigate the center once, we would have gone one floor up. And that means we're no longer discontinuous because now we're on a different floor, right? And that's basically the idea for the Riemann surface of the logarithm function. And similar ideas then are done for other functions. You would always just cut your plane open along a branch cut and then somehow attach more floors so that as you go across the branch cut, you don't go back through a discontinuity. Pictorially, that means that you take your plane, and here's the half plane. Now let's look at the full plane. Well, if we make this into a spiral staircase, then here this horizontal line is theta equals 2 pi, but because we have some vertical translation, theta equals 2 pi now doesn't link up with theta equals 0 anymore, so we don't have that discontinuity. So we can now continue to theta equals 3 pi over 2, oops, sorry about that, and then to theta equals 3 pi, now to theta equals 4 pi, and again, this horizontal line is theta equals 4 pi, which doesn't link up with 2 pi or 0, and we can keep rotating around. And so now if theta is just how far off the x-axis we are plus how many floors up we are, then theta is a completely continuous function on this spiral staircase, and we can continue that all the way off to plus infinity in the vertical direction as well as down to minus infinity. And so the argument would not be discontinuous on something like that. If you want to make that technical, you would take the complex plane with the origin removed and you consider it as a thin sheet R0. I'm not sure why I called that R at this stage, but okay, R, yeah, Riemann 0, that is cut along the positive axis so that when theta approaches 2 pi, theta no longer can reach the theta equals 0 position. That's exactly what we had back here, right? You cut it, you push it up so that as theta approaches 2 pi, you no longer get near theta equals 0. Okay, and now for every integer n, we can find such a complex plane Rn with the origin removed, consider it as a thin sheet that is cut along the positive axis, so that when theta approaches n plus 1 times 2 pi, theta no longer can reach the n times 2 pi position. That's all those other sheets that we attached in this animation on the previous panel. If we now, for every n, join Riemann n and Riemann n plus 1, so that theta approaches n plus 1, 2 pi on R, so that when theta approaches n times 2 pi on Rn, then it approaches the theta equals n plus 1, 2 pi position on the n plus first part of the Riemann surface. And let me say then really quick. Okay, right, so I have to say when here, not then. Know when to say when is something that comes up in public service announcements sometimes, and I would like to emphasize, despite this typo, I know when to say when. Let's see. So the result then is a set so that every point has a unique set of coordinates r theta, and that point then would still be denoted r e to the I theta, and on that set the logarithm function really is uniquely defined by ln r plus I times theta. Okay, just as I mentioned, that is a tip of a rather large iceberg that is certainly quite beautiful also if you are into these kinds of surfaces, and if you like that stuff, I would certainly encourage you to keep reading up on it. But for what we're doing in this course, we just wanted to have a quick indication how this stuff works. The technicalities turn out to be quite substantial, and again there is a trade-off. The theory of manifolds, as these things are also called, is quite beautiful, but the technicalities to just make sure everything lines up, that is quite substantial. All right, with that we are through with this geometric part as to what shape goes where. At least for a little while. We will now talk about conformal mappings as far as I recall, and after we have those, we'll go back and actually apply the way we are deforming certain domains and ranges in order to solve certain partial differential equations. I'll see you there.